said it briefly, but I graduated from here a quarter century ago, it seems. So I was in this exact same room taking classes in professional practice, I believe, where I fell asleep in the back often, which I had no idea that my entire life in the future would all be about professional practice. So definitely, you know, be aware of the things that you learn. I've also had the best time of my life here in Buffalo. And I can talk about it forever, but I want to talk about the work, and there's so much time. So I'm going to define the designer, or what I call 3 types of designers, and how they relate to materials. And it's going to a short kind of glimpse at the work that we're doing at Terreform One, which is a 501c3 nonprofit organization there in Brooklyn, New York. It's about art and architecture. And here we're looking at what I call, you know, the good, the bad, the ugly. And I just gave this talk in Shanghai, and I used Clint Eastwood, just his eyes as the kind of the image from this movie, and it freaked them out a bit, so I took them out. I just leave the text there. But it gets to the point. So we're going to start with the ugly, which is this. This is the first type of designer. Believe it or not, the type 1 designer is someone that takes a regular everyday object or what have you and tries to make it beautiful. That's it. Now I think, and you know, certainly this was an attempt at that, or cobbling a number of things together, but certainly didn't quite work. And if that's the type of designer you are, or the type of designer you want to be, I would think you're not using the real potential and power and the full force of design, especially when you get something like this cobbled together parking meter system. This is type 2, as far as it comes to designers. This is a designer that is so incredibly fabulous, has such an incredible ego, and such a kind of signature process of doing things that you can almost recognize them immediately. It's very selfish. It's certainly something that extolled many of the virtues in the 90s. And you have this object produced from type 2 designers. This is Philippe Starck. This is a gold-plated AK-47 machine gun with a light bulb on the top. I think it sells for about $18,000. Excellent. So I was trained in the academy where we were supposed to get out of school and be the kind of the type 2 designer. And now I think we're seeing something that's about your generation. And certainly something that we're in the mix right now. And that's the designer as hacker, designer as humanitarian, designer as inventor. Someone that just doesn't design another lamp, but questions the entire concept of, do we need another lamp, or coffee cup, or a parking meter system? Can you look at the system holistically, find out the missing pieces, juxtapose the inobvious, and create something different? Not just work as a kind of slave for a client. And this type of designer, the type 3 designer, really represents the big culture that we're seeing now. A lot of DIY, a lot of hacking, a lot of merging different disciplines together, getting the general physics of a project like architects can do, and creating new narratives behind them. Certainly this project here is called the Hippo Barrel. Is a concept for developing nations to help women who have to often carry water a great distance to their home village. Here, this is a very simple plastic barrel that holds about 30 gallons with a stick, or actually a rope. You can pull water a great distance, and it's super cheap and makes sense for those communities. So let me set this up. This is a video of a short video of one of the projects we've been working on that actually talks a lot about what Philip was just discussing there on Skype. So this is called BioCity Math, and it's a very short video.
Zooms in on each of these cities, designed and built built and grown inside petri dishes.
We chose colonies of E. coli as a method of demonstrating exponential population growth. Population density was represented in two different forms of fluorescent E. coli. Red represented future projections of population density, while green represented existing conditions you would find in cities. Biology is technology. Genetic modifications of benign strains of E. coli were carried out at GenSpace, the world's first community-based biotech laboratory. Genes cloned from bioluminescent oceanic animals, such as jellyfish and coral, were introduced to bacteria by transformation. These genes encoded information that would enable our transformed microbes to synthesize either GFP or RFP, two brightly fluorescent proteins. The transformed E. coli were then incubated overnight on petri dish plates containing agar-based media with antibiotics to select our genetically modified strains. Individual bacteria divided through repeated population doublings to produce colonies containing millions of cells. Each selected cell now expressed our clone proteins. We then used high-speed centrifugation to concentrate our colonies of transgenic E. coli.
Stencils derived from CAD files would shape E. coli into specific geometries that would show or display the current conditions in cities. We wanted to move away from the current paradigm of studying population through computation. We wanted a different method to explore how humans might affect the Earth. Cartographers, urban planners, biologists, and architects, all working to think about a map of the near future of human population.
So we work in a very kind of interdisciplinary group. It's actually kind of a heterodox, where you'll get someone like a cell biologist, an architect, a sculptor, and a poet working on projects. And some of the things I'm going to show you kind of blur those boundaries rather naturally. And I think we kind of live in this environment. Also, we work on the large project, which is called the Smart City, which is where everyone comes together to sort of solve that problem, to define it, to move it out of some level of abstraction and reify it into a level of tangible reality. And when I think about the question of smart city, it operates at all scales. As a designer, there's not one scale that you actually work in. Any scale that you operate in has massive consequences, both extra, extra large to super, super small. Actually, Mike and I wrote a book about that, so you can download that at some point later. But the thought is that you're operating at any particular point in the system and you're affecting something else, and the ramifications are large. So when we think about smart cities, you just can't define it at any one particular location. Certainly not time. This is a city that started in 600 BC. It's got centuries of life behind it. It has organic growth. It's seen the Byzantine and the Ottoman empires. It's certainly been through all kinds of different forms of making, architectural and industrial, etc. To call this a smart city would be smart. To say that it is not, it's an ancient, antiquated place that we want to remove ourselves from, I don't think is the right kind of semiotic pulse. This is another kind of smart city model that we look at when we work at all scales. This is actually General Motors, the tall building cluster built from scratch there in Detroit. And this is the kind of the image we start to think of a kind of futuristic glass and steel, elevator-driven smart city where all kinds of ubiquitous technologies are printed throughout and you have this kind of artificial and highly fabricated life. There's certainly elements to this that make it smart, especially the networking, but I don't think this is the kind of vision of a smart city. And this is one of our variations on smart cities. And this is a place that's integrated into the historic or existing city and that has overlays of networks, overlays of socio-ecological needs. And this is a city that's essentially salubrious. It's designed around your health, the function of air quality, waste, food, water, energy, and mobility are all reconsidered, perhaps from scratch or perhaps just retrofitted along the existing city. So we find the Smart City project is a very difficult definition, kind of like painting a watercolor in a stream, but involves all different levels of research, certainly from the material all the way up to regional transportation. We do these kinds of cities often. We make these big models. This is a project that combined Governor's Island, which is over here, with Red Hook. Both of suffering from Hurricane Sandy. We're looking at creating access to a cultural center and then bridging it here to, I guess, an indigent population of folks that live in Red Hook. We're also rethinking materials when it comes to housing. This is a project where the landscape is the home. In fact, there's no distinction between landscape and home. It's kind of like picking up a piece of the earth, wrapping it around, and dwelling underneath it. It's called the Fab Trehab. It's a project that looks at kind of the extreme version of green design or ecological design. It's based off of principles that are 2,500 years old, or it's called pleaching, or grafting an osculate matter to form one contiguous vascular system. You can do this with vines or semi-epiphytes, and you can attach them to large trees, and you have a living structure, a living, breathing structure that takes a long time to grow, but also lasts a long time. It's what I see as a kind of, this is a model we did for the MoMA, a kind of a true organic architecture. Not your grandpa's version of organic architecture, which is Frank Lloyd Wright, still glass and steel and concrete, but an actual living, breathing organism, a part of nature as it is, without modification in this case, being tweaked or adjusted to find a geometry for human use. Certainly the time it takes to grow it is an issue. There's always a curmudgeon someplace saying, I don't want to wait 7 to 10 years for my treehouse, but honestly, we wait 12 years for a bottle of scotch. I think we could wait 7 to 10 years for an entire village grown into the metabolism of a local ecosystem. So we've been working on scaffolds that help shape the geometry of living systems. We moved up to this project, which is more about the sense of affluenza and immediacy we see in American culture today. In other words, you can't click a button and buy our treehouse, but you could click a button and buy our tree ball, or what we're calling our urban farm pod. So here is a rotegrity structure. It's assembled, filed a factory. It's made from a CNC file. It's the rotegrity structure is originally Buckminster Fuller, but you can change the resolution pretty much at any scale to get it to any particular size, and it's all flat packed and easy to ship. And the thought is that you can either hang these from trees or keep them on the beach, put them on your balcony, put them on a rooftop in an urban place, but it's a very kind of compact pod that on the exterior grows all different types of food. Certainly any vegetative species that makes sense based on the desired occupant. And on the inside, be a place where you could be on your cell phone, have a quiet call, sit with a friend, etc., and be at one with nature in the city. This is a view of this is us in the middle of, it's not finished, this is us in the middle of working on it, but you can see we're working on these sub-irrigation planter systems that are there, the geometry fitted to each one of these foam pre-cut mechanisms, and then studying different types of plants and how they would survive over time based on solar income that the ball gets. This is another view of one section that we just finished with the planter just inserted. It'll be a double skin system with a gravity-fed sub-irrigation tract on the top that travels through it. I was also thinking about, I guess we just heard from Philip, but thinking about these fictive narratives and how we have to really embrace them as designers. When I went to school, if you brought up science fiction, I don't know if some of the old profs are here, but it wasn't really something you would talk about. I had to talk about Derrida or Descartes, and they're still relevant. But I think that science fiction allows us the power not to promise, because that's not what it's about, but to imagine in great detail the possibilities for the near future. And designers can do that on the fly. If we didn't have someone like Philip or Jules Verne imagining Earth, the story from Earth to the moon, it'd be very difficult as a NASA engineer under the kind of the rubric of John F. Kennedy to get to the moon, to even start the process. Those detailed stories make a lot of sense once you start to believe in them, or at least want to propagate them, or argue about are they right or wrong. So to drill into one of those thoughts, we were tasked with designing a future car at MIT, and I think I did over 40 of these cars. And we didn't want just a future car. We wanted a lexicon of ideas that would be available to any company, not just General Motors, our sponsor, that would change how we think about mobility in cities, period. The entire 20th century is designed around the automobile. Let's design a technology that fits cities. So this is an omnidirectional vehicle. This one here shows that it'll spin on a dime, the wheels are 360. Actually, the entire car is in the wheel, drivetrain, motoring, suspension. The cabin itself will spin and you can get off or ingress and egress directly onto the sidewalk where it's safe. It makes parallel parking with your eyes closed actually very easy. It's also connected to a computational municipal grid where these vehicles talk to each other and move in swarms and herds of cars. This is another version called the Bit Car. This one is very similar to the past one. It's got the same omnidirectional wheel system, but the frame articulates or stands up, and these cars interlock. So you reduce the footprint. If I was an alien looking down at cars today, I would think they're designed to be parked and take up space. If you reduce that space by compacting the vehicle and interlocking them like shopping carts, you can get about 300 of them on a New York City block, as opposed to 30 or 40 SUVs. So a much different car. They're robotically linked in a stack. You can take the car in the middle of the stack, you can take the car at the end of the stack, and it doesn't tell you things like how much fuel you have. It's a kind of a Facebook on wheels. Lets you know where your friends are, if you need to go to work on time, and it's a shared ownership model. You buy into it like a utility, you don't own that specific vehicle. So this is designed for downtown cores and for areas that we're expecting to get denser and denser with traffic and congestion. Also changing the material of vehicles. I mean, since Henry Ford, we've basically been doing nothing but sheet metal. All kinds of precious, shiny metal boxes that say, don't touch me, don't scratch me, especially if I'm in LA, I'll get very nasty with you. So here are these other thoughts that we could embed them with e-ink technologies that send off social projection, where they track the driver's view wherever you're looking. It forms an aperture through the skin, or it could be just the opposite, completely transparent with a visor that tracks the sun. And the materials themselves would also be soft, a soft car. This is a car that's opposite the Hummer, which is as hard as possible with almost no crumple zone. This is a car made of air bladders and air quilts and ETFE foils that's so light, it's essentially as light as a beach ball, because that's all you need is a canopy when you're driving around, especially if all of the systems that you need for driving are in the wheel. This version that I did is called the Hug and Kiss Lamb Car. It is the softest possible car you can imagine. The concept here is to move in flocks and herds, and it's okay to rub up against other cars and look people in the eye and say ciao and move in this kind of intelligent flock of vehicles. And what do you do if there's a Hummer on the road? Well, these super smart omnidirectional soft cars find the Hummer, they cluster around it, push it off the side of the road as they take over the streets. And that is, in design, we realized it wasn't just about vehicles. As designers, we saw these were incredible energy systems on wheels. They were very big lithium-ion batteries that could absorb peak demand and redistribute charge on the fly. So it became the second layer to the antiquated grids for energy that we find in cities. Thus, another kind of logical system plugged in for these vehicles. We did a vehicle for Shanghai, very similar to this one. It's called the stackable car. The same thing, where we'd have dedicated lanes for higher speed travel. These vehicles do not need to go faster than 30 miles an hour. If you've been to Shanghai, Paris, or New York, 30 miles or 50 miles an hour is just too fast. And the speed limit in New York is 30. Same with Paris. So there'd be dedicated lanes for more high-speed movement. They could park on the sidewalks, and they can go from city core to city core. This is the one that we put into production. Will Lark was one of the guys in our Smart Cities lab that decided to stick with this project for 14 years and produced what's called Heroku. That's the Prime Minister of the European Union in this car that you could buy for 18,000 euros. It spins on a dime, it stands up, etc. I suggest you check it out. But it came from this kind of body of design evidence on how we can rethink vehicles to fit the 21st century city. Other thoughts were kind of thinking about, well, what else could we do with vehicles in cities and still meet some of those material constraints? This is a project called the Blimp Bumper Bus. And this was a fantasy of having the Thanksgiving Day Parade every single day in New York City. If you've ever been there, I've got two beautiful daughters. You see Spider-Man and SpongeBob and about 40 people trying to hold down those balloons. Well, this is a thought that the balloons, controlled by a funicular, would move with ski lift chairs on kind of tendrils where you hop on and hop off and only need to go about 13 miles an hour, and you kind of float through the city. And the point is that occasionally it will bump into a window or a building, and that's fine, especially if you're in your office bored. You look out, the giant kind of blimp bus gently nudges up against the window, and then off it goes as it meanders down the streets. And then all of these systems connected and talking to one another. So this is a project about soft mobs and smart dots. And I think these are where some of those, the sheep cars and the blimps and other standing vehicles and energy systems all connect to a highly connected municipal computational grid. But what's most important about this is actually not all that new stuff, but this stuff here, which is the best way to explore a city. The most fascinating, the most interesting, and the most comprehensive way to explore your urban space is by the interface of the foot. Walking and pedestrian or walkable cities are absolutely crucial, and certainly bicycling is an amazing technology and a great way to discover cities and is about as green as you can get. So we definitely think that there's a continuous future for these kinds of systems. So how do we teach all this stuff at Terreform One? Well, or how exactly do we operate as a kind of a lab? Well, we do it in many different scales with different disciplines working simultaneously. So this is Carlos Barrios, another doctorate from MIT, and he's teaching CATIA, parametric modeling actually, to a group of scientists so they can get some understanding of the dialogue we work with as architects in master geometry. And he's doing that with wooden blocks. So he's teaching these guys, the biolab guys, how we work with CATIA. And this is a biolab, that's Oliver Medvedik. He's our chief scientist. He was my roommate at school. He was at the Harvard Medical School, and he works at kind of bridging the art of design, and certainly architecture, into the world of biology and synthetic biology. And does that in a very DIY fashion in an open lab called GenSpace. We also teach how to build your own machine, because it's a much different thing. If you make your own software or you make your own machine, you have a new relationship to that artifact. So here we are teaching guys how to make a thermoformer from equipment you would find more or less anywhere in a domestic kitchen. And once you make objects in this thermoformer or vacuum former, you have a new understanding of the whole device and have an incredible kind of skill with something like that. We also teach a lot of urban gardening. This is on top of the Metropolitan Exchange building. These are one of the courses we run at one lab. This is running the pleaching course that looks at making homes from living trees. Here we're grafting poplar together into a specific geometry. Or teaching about lightweight soils that need to go on roofs if you plan on doing urban farming. Pectin impregnated or clay-based soils are super lightweight, meet the demands of the roof load, saturate the amount of runoff that you expect, and you can actually grow food there. Or actually teaching things like phytoremediation, which is something you could expect on a drawing, but it's a lot different when you have a green thumb and make something yourself. So this is gray water from your sink, dirty water from your sink, going up to the roof, and then filtered through this inclined plane with the appropriate plants, and cleans it and makes it potable water at the end. After doing this for years, we got a massive grant from the governor of New York State, Cuomo, gave us $46 million. We teamed up with the group MacroSeek to move to the Brooklyn Navy Yard. Here you pretty much were in that space. And bring in this kind of new creative class to work together under one roof to think about where design, engineering, invention, art all kind of happen. So this is the Navy Yard itself. It's 300 acres plus of essentially fallow land in New York. This is the building that we had purchased with that money and changed the core and shell. This is just one view from the inside. This is actually after the steel was fixed. So it's roughly 80,000 square feet in that space. And this is a photograph from a couple of days ago showing the core and shell is finished. We should be able to move in, I don't know, 6 months, I want to say, depending on how fast those union contractors can work. But this will be a hub of activity where all kinds of things will be going on. So we'll have spaces for ideation and crit rooms, assembly, fabrication with water jet, and we have the highest resolution printer with EOS printer, 3D printer on site already. Low-tech shop equipment. My dad was a cabinet maker. I definitely can't. I express learning from the wrist down, and certainly a wood shop is important. And then all kinds of areas for either businesses or academic venues to work and merge together in this open floor plate. This is called the New Lab, and we do a lot of the teaching in there. It's the one lab. That's showing you a detail of some of those spaces. There's dedicated spaces where are private for you to work on your laptop, but many of the zones are shared. And certainly we have a kind of an auditorium for TED-like talks, presentations, and exhibitions. And we have this kind of philosophy of what sort of folks fit in this new lab, which is this kind of represents the center of the Renaissance going on in Brooklyn, New York. And I didn't realize this, but this diagram does look like Mickey Mouse. So if you're going to point that out, fine, I'm on my head. But essentially, this is the idea of the urbaneer. And this is a person that cares about their city is certainly some kind of designer or inventor or maker and wants to do something. But what are the kind of philosophies behind that? Well, I think it's a combination of these two great figures, which is Jane Jacobs, who is the kind of the community activist, the kind of grassroots approach, the kind of power of the pen that changed how we think about these large corporate structures. Jane Jacobs is a hero of mine, absolutely. And another, her nemesis, another individual named Robert Moses, who is very difficult, and a person that built something like 8 times the size of Rome per year, commanded a quarter of the entire United States budget, and was building bridges, tunnels, housing complexes, parks, etc., all kinds of things, and doing this with this kind of power broker mentality, this kind of top-down authority, and spent a lot of time fighting with Jane Jacobs. Well, it's my belief that the two of them weren't actually, they were fighting in public, but behind the scenes, they were having an affair, and the common broke, and they produced a love child, which was Frederick Law Olmsted, who was the combination of both of these figures. I know that's not historically accurate. That's not true. Olmsted was able to achieve things that made sense to the community, cared about nature in the city, cared about the kind of programs and functions that happened, and certainly was able to get very, very, very big projects accomplished. So we do this a lot thinking about the city that we're in, Brooklyn, New York. Here's Brooklyn as it used to be, a lot of green space, but essentially none of it, there's no inhabitants at this point. And then Brooklyn that you find today, where there's some green space, but notice the zero here, none of it is what we call productive green space. Space that deals with waste, food, water, energy, mobility, fit into a city. The city is made up of materials, it's made up of a metabolism. We should be self-sufficient, we should consider an infrastructure that supports the population that's in it. So we do these large-scale models that look at what that city might be like if we adjusted it to meet those demands. This is drilling down into one specific park. This is a park that is a productive green space, not just a green space where you play frisbee or walk a dog. And here we're making a spectacle out of the biofuel reactors. They release in the summertime a fine cooling mist so you can hang out underneath them and picnic or what have you. In the wintertime they radiate a little bit of heat, but they're also producing biofuel and biomass to be used later on in the city. And this view of yet another version of a smart city is rethinking the idea of centers of cities. So here, I would say traditionally, if I'm going to zip through the entire history of planning, cities were designed around usually ecclesiastical structures, such as churches or mosques or what have you, or they were surrounded with fences for military protection, etc. But there'd be some kind of notion of religion or spirituality as the center of those cities. Then if you zip up centuries later, the center of our cities are skyscrapers that celebrate corporate power, that celebrate capitalism, that celebrate our technology and our success as a nation. And that is propagated all throughout Africa, Europe, America, South America, etc. And we think that's the only version to go. We're thinking the future smart city, it won't have an exact center. It'll have many centers. And in those nodes, there would be a celebration, not of religion or corporate structures, but a celebration of infrastructure working fantastically. In this case, you can imagine a waste-to-energy plant being the node in this particular center, converting it and doing it at a high rate of efficiency and supplying it to the needs of the population that's there. So do a series of these models. This is actually the Brooklyn Bridge. That's the Manhattan Bridge. We preserve 85% of the building stock and do a lot of adaptive reuse and inset that productive green space. We also think about adaptive reuse as a form of material that you can find in large-scale objects. So this is master planning with objects. So here we've taken ghost fleets or ships that have been decommissioned by the military. We've cut them up as a proposition for a buffer zone between the water's edge in cities and programmatic space used for people. So here's what they form, a new kind of territory for aqueous life, artificial reefs, etc. This is where we fit them out and build them into our edges over time to absorb the impacts of climate dynamics and the sea level rising that we're expecting in many American cities, if not across the world. Create these buffer zones that are not for people and not for nature, but both simultaneously, using the materials of kind of former war machines. Here they are over time as the heavy kind of tidal flow of the river builds up the sediments and they slowly disappear and decay into this kind of new edge of the city. These are other views of this. Took this to the Brooklyn Navy Yard. These are a series of dry docks that we've repurposed with similar usage. And here we also make no distinction between the water's edge, nature, and where architecture exists. So this is kind of one singular model that represents all different kinds of metabolic flows. The functions would change, and the industries would change, but the actual, the physical bits are at the best possible way attempted to be fully integrated to all aspects of that plan. This is actually one section of this master plan that we had done that we're now converting, oh sorry, this one, converting into those giant buildings for the new land. Other things we like to do is explain to the everyday person, like Homer Simpson, what kind of damage we are doing to the planet and what happens with all this construction and carbon loading in the atmosphere, and taking the abstract kind of numbers and giving a kind of a visual, through the power of design, a visual implication or folly that does that. So we call this project 1 Hour Tower. It is 36,000 tons of waste produced every day in the city of New York. I don't know what 36,000 tons of anything looks like. This is 1 hour's worth of it. It's bigger than the Statue of Liberty. And we use that as a kind of a model or a folly so that others can get on board, at least think for a moment, not about sports or education or war or whatever is in the typical mindset of your job or the economy, but about the kind of the resource extraction that we do and the scale that we do it in every single hour. These are machines that compact waste in New York. We propose modifying the jaws to make puzzle-fitting geometries of that waste into some of these follies. So we take that waste and make them into these architectural shapes. One of the projects we were commissioned for the Metropolitan Museum of Art is taking e-waste, or styrofoam waste, and converting it into these follies to explain to folks how much they throw out when they have all this packaging material that comes in their speaker boxes, microwave ovens, refrigerators, all of the stuff that gets delivered to New York City daily, and how we try and dispose of it and throw it out. So this folly represents a 30-second flash of e-waste in New York City, believe it or not. It had to be an interactive piece, sorry. So we had a bunch of 8-year-olds take it apart. They're very violent. The idea here, though, is that we want to explain to folks how incredibly wasteful we are with styrofoam, and are there some alternatives. Also did this in Darmstadt. We produced these little Wally-like robots that were deployed throughout the city, QR tags, to show people the amount of waste they produce in a given day. There's this one was 30 feet tall. Actually, in the center square, we put this out. This is not a doctored photograph, but we put out these volleys, and they were all over the city. And then the Germans came with the sanitation crew, and they kind of walked around the pieces and said, are they trash or art, or trash or art? And I guess they decided it was trash, and then we ran out there and explained to them, no, it's art, it's about waste in cities, and they said they know. So good for them. Here's a replacement for styrofoam. It's called mycelium. Some of you may have heard of it before. We've been working with it since 2007. It's taking cellulosic waste you find, let's say, in farming, and converting it into a mushroom substrate, or the root base of reishi. In this case, it's a mushroom. This can absolutely replace styrofoam. It has all the same properties, no allergens. And you can see in 7 days of growth here, it busts out of its mold, this plexiglass welded mold, in the incubator and forms a very rigid styrofoam-like structure. We've turned into Microform, which is another project. We're looking at Tetris-fitting geometries of this living mushroom substance to make all kinds of things, adding another high-embodied energy material such as aluminum, which is an excellent material because we can recycle it into infinity, add it to the mycelium system, and you can take care of a lot of the tension and shearing forces and insulation systems. Here is a tower made from just the cellulosic waste we throw out in New York City. This is a 53-story skyscraper every day in New York. The exterior made from just the kind of the organic waste that we throw out. And then we thought of a kind of more practical thing that we could do with these kind of synthetic biomaterials that we've been working with. So one of the things is, from a poet in our group, said, let's find something everyone can relate to. Let's make a chair, a biosynthetic chair. Great. I know architects love making chairs. Clearly, they always do this. So here's the history of chair design in one slide. This is 19th century and earlier. This is a bespoke handcrafted object where there's a relationship from the maker to the thing that was finally produced. And we have the 20th century, which is designed for modularity, plastics and steels, unitized volumes, designed at high throughput, made in the zillions, and basically represents Gropius, Charles and Ray Eames, etc. And we're still in this mentality. The 21st century chair is something that is grown in a lab or produced in vitro or made up of completely actual organic compostable materials, lasts for 5 to 10 years, and when you throw out this chair, unlike throwing out the previous 20th century chair, which when you toss them away, they just end up in a landfill, this one goes into a garden and feeds thousands, if not millions, of other organisms. So we call this the Gen 2 seat, genetic generation seat. It's a combination of the mycelium I showed you before and another substance called acetobacter, or bacteria express cellulose as a material. The two of them were combined to form one kind of biopolymer. I think that architects are always trying to combine things, and we did a good job. Here's one of the early versions. This is to give it resistance against water, hydrophobic, and then design that chair. Here's one of the versions. That's the parametric model. That's the chair itself. We imagined it would be a chair for kids first because, well, it's healthy. It's a part of the environment. Children can eat the chair if they want to. It doesn't taste good, but this is where parents can start to see the effect of synthetic biology and DIY designing and start creating these kinds of things. We took it a little bit further. We created a bamboo egg crate scaffolding and then inserted the mycelium with the acetobacter here. And you see we start doing it at a larger scale. We made a chaise lounge for adults instead of just the kid chair. So this is a triply curved geometry, shaping a mushroom into a triply curved shape. And it grows into the scaffold, stays there, and you have a chair that's both synthetic biology and also industrial design at once. That's another view of it. That's the kind of shape we got to. That's us seating it, and that's it in growth stages right now. So it's not finished because we're working on 3 of them, and it will premiere in May 24th in a gallery in New York. So I have to, very cool. That's basically, I can show you the shots that I took with my cell phone. And then I guess the last few projects, because I only had so much time here, I'm going to end on our biolab and this meat house project, which is a little bit controversial. But it started with thinking about, can we print cells into a geometry? And yes, we can. There was a paper done like that at Harvard Medical School. This was another version done by David Rue and some other groups, but it is a RepRap printer, or an open source 3D printer with everything you need in biology here in a sanitary syringe. So you can control the syringe output, print the cells into a shape, and start getting different objects. We also teach classes in modifying inkjet printers, either Panasonic or HP. But you can modify the printers and get geometries that fold up, from printing cells, in this case an extracellular matrix from pigs. So it's mammalian cells, and you can make these kinds of shapes. This is done in regenerative medicine. It's about 15 years old as a technology, but it's great when architects hear geometry, we can get a handle on doing this, especially a DIY version. And this is a bladder that's shaped for a patient to be replaced in cancer surgery. This is a proposition for making a home out of these same materials. This kind of mammalian cells blown up to scale with the equipment that we have produced. And that's on this side. This side is a typical stud wall section. This is my favorite section in the history of architecture, maybe because I drew it, but because it's living cells, and it's got supercilia here for wind loads, fatty cells for insulation. Doors and windows were made of sphincter muscles because we can, and we thought what else would be completely natural. We know well, this is one of the views of the geometry. It could look like anything. This is a question of what should a synthetic biological home look like. And because it's an architecture school, and I learned about Louis Kahn here when I was a student, I would say that Louis Kahn would talk about what the brick wants to be. And there's a kind of a nature implicit in that brick, given to us by our hands, a module of the human body, to fit against gravity or with gravity to create fantastic structures. And that makes sense for centuries of architecture. But if architects are working at the scale of cells and are printing them, and the geometry is anything you want, it becomes very difficult to figure out what that home might be. There's a field of genetics that works on that morphology. It's called HOX, but it's very new and we're not sure exactly how to control it, although some of that is controlling the wings of a butterfly or adding colors, etc. So here is the Meat House project. We had a big show in Prague, so we decided to put the Meat House in front of the cathedral so religion can confront it and they can deal with that as a future of architecture. Anyway, that's a very short view of some of the work we do at Terreform One. Thanks very much for listening, and I guess we'll do questions at some other point. But thanks, guys. Thank you very much.
So, Deborah Chung earned a PhD in material science at the MIT. She's currently teaching in the Department of Mechanical and Aerospace Engineering at the University of Buffalo. Her research broadly includes a variety of composite materials, such as electric, thermal, and structural materials. With her field of research, her presentation will be an introduction of multifunctional structural materials for the built environment today. Thank you.
Thank you. The smart structures, whether buildings or bridges or tunnels, can be very exciting for future cities and not that far into the future. And to get that smartness, there are two avenues. I call them extrinsic smartness and intrinsic smartness. Extrinsic smartness means that the structural material itself is dumb. It doesn't provide that extra functionality, whatever it is. It's just structural. Okay? And in order to render the smartness, you have to embed or attach certain device. Okay, that's extrinsic. Intrinsic smartness means that the structural material itself can provide that extra functionality. Okay? The advantages of intrinsic smartness over extrinsic smartness include low cost, high durability, large functional volume, as well as absence of mechanical property loss. If you're embedding a device in a structure, obviously you get mechanical property loss. If you're just attaching the device on the structure, chances are the device is going to get detached in maybe a couple of years, and you have to do it all over again. Okay? I'm going to focus on materials because they constitute the foundation of technology. You know, whether electronic, aerospace, automobile, energy, whatever, you've got to start with the right material. And in fact, materials mark the history of human civilization. Stone Age, Bronze Age, Iron Age, every age came by because of the advent of a certain material. And it's exciting to develop new materials. It's like being on the driver's seat of technology. So I'm going to focus on multifunctional structural materials for the built environment. Okay? That is, they are structural materials, but they are providing more than just a structural function. Okay? And I've been at this kind of research at UB since 1993. It's been a long time, and I'm just going to give you a snapshot of the kinds of directions that we have been taking. Okay? One of the functions is structural vibration control, that is, vibration damping. No structure likes to vibrate. Okay? One way to counter the vibration is to use a big mass and let the mass move. It's called a damper, and this is a multi-story building. And it's just like on the subway, if the car sways this way, your body moves the other way to counter it. And so you use these big masses. Here is one big mass on one of the floors high up, because high up, it sways more. So this big ball gives what's called a tuned mass damper. This is in Taiwan, and this is that big ball. And it actually moves, thus doing the damping. And in addition, the green actually includes further damping material. Okay. Another way to counter the vibration is base isolation. Okay. That is, the building's base is on some rubber kind of bearing, so that the whole building can just horizontally sway, as in the case of the right picture, in contrast to the left picture where there's no such base isolation, so that the building actually experiences high vibration and in the upper floors, and if you just get upper floors sway more than, and then the lower floors. And that kind of bending is terrible for the integrity of the structure. But if you do this, then you get all the floors experiencing the same movement. And that isolation rubber bearing involves rubber sheets and steel sheets. Related to vibration damping is sound absorption. We have a lot of noise in urban areas, and we need to kill that noise. And so sound absorption materials, whether for the walls or the ceiling, are needed. And such materials are like big blankets. They're kind of voluminous. It'd be nice if we can use the structural material for vibration damping as well as sound absorption. That is, maybe instead of that base isolation, instead of that big mass moving around, we have this good old structural material that you use to make a building, and that material is unlike the usual structural material, that the structural material itself can do the job of damping. Another issue is structural health monitoring. We have a lot of structures that are degrading because of old age, like this concrete deterioration. And Band-Aid obviously would not work, to mend the crack. And ideally, you would like to have what's called self-healing. That is, the material, when a crack or some kind of defect occurs, it automatically heals, just like a human being. If you have a cut, it automatically heals. That would be super. However, the technology is not ready yet. People have proposed using bacteria to provide that Band-Aid, to mend the cracks. But it's a technology to monitor its moving. Another issue is energy. Buildings consume a lot of energy, losing the heat from the roof, the foundation, the sides, and the windows and doors. And thermal insulation is obviously very important. But the thermal insulation that we are using are all non-structural materials. And they're mostly like foamy material, which is very soft and bulky. It would be so nice if the structural material can be increased in the ability to serve as thermal insulation. De-icing in Buffalo, we know how important or how troublesome the ice can be. And it'd be nice to have automatic de-icing when there is snow, and that can be done by heating, using cables, which is the wiring for the heating, and you melt the ice by the electrical heating. And same deal for electric underfloor heating. And here, for de-icing as well as anti-icing of the walkway or driveway. And all these technologies currently in the market, they use embedded cables, electric wiring. And actually, that technology is old and not very effective, not very efficient. It takes a lot of wattage to do the heating. And because of the high wattage, you have to insulate it. It's too dangerous to touch it with your hand. However, it's possible to make concrete just electrically conductive enough so that it actually becomes even more efficient than the metals for doing the job of heating. And that's a technology that's already ready. And in UV, in my lab, we did a large part of that work. A related application is electrical grounding. Any building needs electrical grounding, and they have electrical metal conductor lines, all over the building. And such grounding is also important for lightning protection. In lightning, you really have charge coming down because of the lightning, and you have to let the charge move to ground. Right now, people don't use the structural material to help the grounding, but actually, electrically conductive concrete can do that job. Now another issue is energy generation and energy storage, so as to obtain what's called zero energy building, which refers to a building that consumes less energy than what it generates. And how it generates energy is usually by renewable methods such as solar panels. Okay. So you see the solar panels here. Okay. And here is, you see the solar panels again. Now, but in solar, you just generate the electricity when there's sunlight, and when there's no sunlight, it doesn't work, right? So when there's sunlight, you better store that generated electricity. So electrical energy storage has to go hand in hand with the energy generation. And right now, batteries are primarily used for the energy storage. Okay? Now, it'd be so nice if structural material can do the energy storage, and structural material can do the energy generation. Now, the reason why structural material is wonderful is the building is almost all structural material. We have a lot of material to serve you. Okay? So if you can use a structural material, whether for damping or for whatever, you go a long way because you have a lot of structural material available for your use. Okay? And a particular direction that UB is special for is to use concrete that is able to act as a balance. That is, it's a sensor of the load. And so you can use the concrete in a multi-story building and sense the number of people in a room just by weighing each room. Okay? And one can use this room occupancy information in real time to control the heating, the cooling, the ventilation, and the lighting in order to save energy. A lot of energy is wasted in half-empty buildings right now. Okay. And this is a technology developed in UB, and it's ready for implementation. A related application is building evacuation monitoring. So as certain fire or whatever happens and the building is being evacuated, you can use this same technology to constantly track during the monitoring how many people are left in each room. Again, related to this is the application of building security monitoring. Right now, people use cameras, and the cameras can only look in certain places. You know, people don't want to lose their privacy. But if you use this weighing method, you can detect an intruder. You can zero the building at the end of the workday, and when somebody comes in, that somebody weighs something, and you would know that somebody has come in, and you know where that person is. Okay. Yet another application area, totally different, relates to electromagnetic radiation, like microwave and radio wave. It turns out that such wave can really damage computers, electronics, transformers, and so on. And our lives depend so much on electronics. You know, just like a computer, if it goes crazy, you know, we can have certain disasters. And so one has to shield protecting the electronics, also shielding the radiation sources so that the harmful radiation would not get out of it. Cell phones actually is an important source of radio waves, and all sorts of electronics, like transformers, also emit those waves. And here is an example of a building where they have a big transformer on the 14th floor vault, and on the floor of the 15th floor, they have in these three areas, they have the shielding material. Okay? So they want to shield in both directions. And this is a shielded room. You know, we unshielded are very often needed. And this is a shielded room obtained by using metal, it's like wallpaper on the floor, all electrically conductive. Thank you. So as to make the whole enclosure that's electrically conductive, and that is called Faraday cage. Okay. Now it looks easy in technology, but there is one difficulty, and that's the door. You see a door here? Okay. The door has edges, you have to open the door. So you have to have a hinge, for the opening of the door. And you don't want the shielding to get leakage there. So you need to have electromagnetic interference gasket, a material which is resilient so that it's like a cushion for the ceiling, like a gasket, but then it is itself very good for shielding. And that turns out to be right now the biggest technology barrier. But it's the most challenging aspect of EMI shielding material is the gasket because of the requirement of resiliency. Also, EMI may cause cancer. A lot of people have said, I have a relative who said, that the cell phone caused him cancer, and he's passed away now. Another related issue is close lightning strikes being generated. Those lightning strikes can generate electromagnetic pulses. Electromagnetic pulses are abbreviated EMP. Those are even more intense than the radiation emitted by those electronics or cell phones. That can be really damaging to equipment installation as well as buildings. And in the case of a nuclear explosion, particularly if it occurs very high up in the sky, like a few hundred miles up there, if it's so high, the footprint can be the whole of America, and the whole of America can be blacked out. So people are very worried about that. Okay. So shielding structures, especially buildings that are very, very well shielded, is called for. Stealth plane, we all know that from military, but now they are having stealth building. This is in California. And the stealth means it cannot be detected by radar. And, in bombing, they use radar to guide the bomb. And I guess they don't want the building to be bombed. Another area is we have a lot of old buildings, and tearing them down, or even tearing down a beam or a column is expensive. To replace a column or a beam, that's a lot of work. So retrofitting is called for. Carbon fiber is famous for its high strength and high stiffness, and here you can see this beam of this building being patched by this carbon fiber retrofitting. And shown here is a column, and you have the carbon fiber epoxy wrapped around, and that is very effective. You might say, oh, carbon fiber is expensive. Yes, it's expensive, but it is less expensive than tearing the column down and building another column. Now, carbon fibers are not only mechanically strong, they are electrically conductive. They are also very good in shielding. They can give you the de-icing capability too. Just stemming from the conductivity, carbon fibers can do a lot of things, and they can be woven to have fabric. The carbon fiber provides structural, sensing, heating, as well as shielding functions. It's interesting to actually use those retrofits to do extra functions. Now, because of the work here at UB started in 1993, we've got a lot of stuff going on. I'm going to summarize a few of the technologies that we have developed, technologies that are relevant to buildings. We have made pioneering development of multifunctional structural materials, including cement-based materials and continuous carbon fiber polymer matrix lightweight composites, with functions including sensing, damping, shielding, heat dissipation, de-icing, and energy storage and generation. Okay. Again, I'm emphasizing we are tweaking the structural material, not embedding devices, not attaching devices. We are tweaking the structural material itself so that it's not only good structurally, it can deliver those extra functions. Particularly well known is my invention of smart concrete, also called cell-sensing concrete, that was back in 1993. And then in 2001, I gave the first report of structural capacitors. That means a capacitor is an electrical energy storage device. And we make a structural material, namely carbon fiber epoxy composite, make that structural material be capable of acting as a capacitor for energy storage. We also made pioneering development of electromagnetic interference shielding materials, and since 1989, including the 1995 invention of nickel nanofiber with exceptionally high shielding effectiveness, and the 1996 discovery of exceptionally high shielding effectiveness in flexible graphite made from exfoliated graphite, and the 2003 discovery of high shielding cement-based materials containing coke or steel microfibers. And we also made pioneering development of vibration damping materials, and since 1996, and including the 1996 first report of silica fume cement-based materials for damping, and the 2010 invention of high damping cement-based materials containing exfoliated graphite, and the 2013 discovery of exceptionally strong viscous character and elastomeric behavior in exfoliated graphite. Okay. So let me just give you a little taste of the kinds of data that we have. Concerning self-sensing continuous carbon fiber polymer matrix composites. By this I mean structural composite having its electrical resistivity changing with strain or damage, so that the composite, the structural composite, is itself a sensor of itself. Okay. And to measure the electrical resistivity or the resistance during bending of a beam, the beam being the composite, we can put electrical contacts on each of the two opposite surfaces. Upon bending, one surface is under tension, the other surface is feeling compression, and so you can monitor both surfaces in terms of its strain and damage separately and simultaneously. And upon reversible strain application, that is reversible deflection, we found that the resistance on the tension side would increase every time you flex, while the resistance on the compression side would decrease every time one flexes. And so this is the compression side, so it increased, this is the tension side, so the resistance increases every time. But note that the baseline resistance gradually shifts upward. That's an indication of minor damage. Okay? The reversible resistance change gives you the strain effect, reversible strain effect, while the irreversible resistance change gives you the damage effect. So one can simultaneously monitor both reversible strain as well as damage using this structural composite. Now the damage in these laminates is most commonly at the interlaminar interface, that is the interface between the adjacent laminae or plies. Okay? And this is shown are two plies with the fibers 90 degrees from one another, and this is that interlaminar interface. And we have developed a method to actually measure the contact resistance of that interface, the two-dimensional, that interface resistivity, and this is the method we've developed. I won't talk too much about it. And we found that this interlaminar interface is a wonderful sensor of minor damage. This is impact sensing, measuring that contact resistance and seeing that that contact resistance drops irreversibly every time you impact it. And is so sensitive that even 0.8 millijoules of impact energy can be sensed. And the reason for this drop in the contact resistance of that interface upon impact is because of the irreversible increase in the degree of fiber-fiber contact across that interlaminar interface as you impact from the top. And when the fibers touch more between one ply and the next door ply, the contact resistivity would decrease. And this same interlaminar interface turns out to be a wonderful sensor of temperature as well as thermal damage. When one cranks up the temperature, the bottom curve is for the temperature, the upper curve is for that contact resistivity of that interface. Every time one cranks up the temperature, that contact resistivity decreases. And that's because the higher temperature allows greater chance of the electrons to jump across that interlaminar interface, thus lowering the resistivity. And so the material becomes a temperature sensor. But as you crank up the temperature to this level, you see a vertical spike. If that highest temperature gets even higher, you see the vertical spike and the aftermath even more, and here even more. Okay, so very sensitive to both temperature and thermal damage. And another nice thing about using that interlaminar interface as the sensor is that you can have a two-dimensional array of sensors, so that you can have two-dimensionally, spatially resolved sensing. One of the techniques that we use for tweaking the composite is to add certain nanofillers to the interlaminar interface. And by doing that, we have been able to increase the thermoelectric figure of merit, dimensionless thermoelectric figure of merit by 4 orders of magnitude by putting certain fillers in between the laminae. And that's the first time that anybody has reported to turn a structural material into an electrical generator. In this case, it's a thermoelectric energy generator. In the area of vibration damping or sound absorption, there are 2 routes. One is passive control, the other is active control. Passive control means you just use the right material and it's going to dampen for you. Active control means you have to use a sensor and an actuator in a synchronized manner. That really is very expensive. So passive control is really the practical way. People have a wrong concept that they think, oh, well, rubber is wonderful for damping. In fact, rubber is no good because it's too soft. It's only a cushion. It cannot kill mechanical energy. And we have developed structural materials, stiff materials, that are good for damping. And when I first presented the use of structural material for damping, that was 1996, people laughed at me. They said, oh, damping has to be using something soft. Structural material that's stiff, no way you can get damping. But now nobody laughs anymore. I achieved that because I don't use the rubber mechanism. The rubber mechanism is bulk viscoelastic deformation to consume the mechanical energy. My technique involves slippage at interfaces within the structural material and having a lot of interfaces. The interfaces allows that slight slippage during vibration, and that's friction involved, and it kills mechanical energy. At the same time, I can engineer the interface so that they strengthen the material. So you can have a situation where you enhance the strength and stiffness, and at the same time, enhancing the depth. And both things being enhanced, that was what those people could not swallow at that time. So I developed concrete with unprecedented damping ability, and this is the fraction of energy dissipated. And when you have no additive, it's very little. The fraction is very little. With silicon fuel, it's much better. But most recently, in the last few years, I invented this graphite network as the additive, and the fraction gets up to 0.72, which is really very, very significant. Now, why electromagnetic shielding? I said already, you want achieve shielding up to 130 dB, which is the highest you can even measure. In particular, we have invented a nickel nanofiber, which is still, that invention was around 1995, and it's still the record in the most effective filler for providing polymer-based materials that are good in shielding. If you are interested in more of the detailed data and the science, you're welcome to look at my books, Composite Materials, as well as Functional Materials. And I'm happy to tell you that the world is noticing us in UV. Okay? And the numerous publications that I have are receiving lots of citations, as high as 1,000 per year. Okay? And various countries have noticed us, like in China. They invited me to talk. And China is building a lot of things, so no wonder they're interested in concrete technology. And I went there, and about 1,700 people came out to listen to me. And in Spain, they are interested also, and they gave me an honorary degree, doctorate. And also, I helped them start a new doctorate program on sustainable construction. It's an interesting ceremony. It's not like a wedding. Interesting. And the American Carbon Society also recognizes what's been done at UB, and they gave me an International Research Award. And it just turns out that I'm the first woman in the US to receive this award. Yeah. And in the award ceremony, I said, I am God's design piece. The reason why I said this is when I look back in my history, my personal history, it's really God's design. I was born and raised in Hong Kong, and in 1969, the first lunar landing occurred. I was near the end of my high school days, and you can now calculate my age. And I was so excited, and I said, I want to go to America to study engineering. And indeed I came, looking like this. And I went to Caltech, California Institute of Technology, and became actually one of the first four first woman graduates of that institution. And after graduation, I went on to MIT for my PhD degree. And in MIT, I chose a research topic for my dissertation, which involves the chemical change of graphite, so that the graphite becomes a metal. And that is so rich in science, and it became a fashionable topic in science in the 70s and 80s. And very soon, I became a world authority on this subject. And I continued this line of research after graduation for about 10 more years. But then, I noticed after that 10 more years, that my only field of expertise started to decline, because the application didn't quite work out. So I was my first major challenge in my life. Actually, at that time, I already became a full professor at UB. I could stay on and publishing in this withering field. Nobody would fire me. But I decided that life is long, and I should do something different. But what other thing to do? That's the big question. That was my only field of expertise. But then for some strange reasons, and I think God did it, my interest just naturally changed. And I got interested in concrete, something I had never mixed, something I had never studied, and I got interested in that. But my background actually is electrical stuff, okay? Not concrete stuff. And so I started studying concrete as if it's an electrical material, electronic material. And again, people found that too strange. Nobody in the concrete field would study concrete as if it's an electronic material. But because of this very strange direction of investigation, I ended up inventing smart concrete, which is the self-sensing concrete that I talked about. It contains a little bit of short carbon fibers, so that the concrete itself is a sensor. And nobody before my invention has even dreamed of making concrete itself be a sensor. And one of the applications need monitoring, but there are many other applications. Okay? So when I look at this history, I'm just amazed. It's not my design of my life. And I think that everybody is in the same shoes, you know. Everyone has got designed matter. That's the title of this symposium. In fact, anybody that has made a baby knows that it's not you're being smart that you can make a baby. The whole process of making a baby is just a miracle. Okay, it's a tremendous design, and the DNA embodies an intricate design. Everyone has a different DNA, right? And it's a computer memory, and it reflects a tremendous degree of intelligence in that design. Now, I'm a pianist, 2.5 months old. I was faking, but it was not easy just to sit there. But I really play the piano. And I've performed even in UV. And this is in Hong Kong. And nowadays, people try to make robotic hand, right? And it's not easy to make the fingers move and so on. But that's really far away from having the hand be able to play the piano. It'd be very, very difficult to play the piano using even a future generation of the robotic arm. You know, our hand anatomy is just another marvelous design piece. The robotic hand is just no way near that level of intelligence. And when you see a bird, I'm interested in aerospace engineering too, and I'm amazed by the bird. It doesn't need an airport runway. No airport runway. It flies down and grab a branch. Very happy gripping onto that branch. You know, no aircraft can do that. So there's a lot of design, a lot of high technology, really high technology that we engineers and scientists should learn from. And if we know how the 4 seasons came by, it's because of the north-south pole being at an angle, and you have the Earth rotating around the sun. So you have the 4 seasons. And that's another level of design that's super, super intelligent. The speed of light, this particular value, the electronic charge, this particular value, and Einstein knows this really, really well. And these different values are all called physical constants. And Einstein said, God does not play dice with the universe. Okay? All these physical constants being those numbers, not 1% off from these numbers. If it's 1% off, we might be all burned because it's too hot here, or frozen because it's too cold on the Earth. And so it's a tremendously intelligent level of design work that we should really lift up our imagination too. I'd like to close by this statement. Easter, Sunday is Easter. It says Easter is a time when you realize you are truly loved. So happy Easter to you all. And that's the end of my talk.
Computing and proprietary software
from Texas, saying that you're going to destroy jobs and, this is going to be a terrible thing because, you're going to introduce all these humanoids onto the site. But as soon as I emailed him back that you're going to make more money, it's going to cost less time, you're going to save on health insurance, I didn't get any emails after that. So apparently profit for them is really good. Our first initial prototypes were basically simple leg-based robots. The idea here was to try to develop an on-site construction tool that had extreme mobility, that would be able to wander around, pick up things, and those can be coordinated in very complex ways. So we just started off learning how to walk, and this is a robot just walking with a stairway carrying 3 bricks. We moved on then to a larger scale robot, which is now at the computer science department, being programmed by computer science students, and this is done in collaboration with Kartik Dantu and Nils Knapp, both really amazing faculty that have had great fortune of meeting and being able to work with. This is just a quick shot of the robot storing up so it can be compact and maneuverable and movable. But then I've always, my wife complained, well, Michael, now you're just doing robotics, where's the architecture? And so that kind of got me really mad. But then I realized, wait a second, but maybe the robotic system is in fact the architecture. So this is the beginning of the next phase of our work, where we're developing this thing called the loft machine. And the loft machine is really just a floor, an automatic floor that made out of simple pavers. And the intention here is that from a single complex robot with a lot of dexterity, mobility, and intelligence, could possibly take that floor and assemble it into different architectural components, including stairways, tables, walls, rooms, columns, chimneys, etc. And then you could basically build any component that you want through this kind of automatic system. And the idea here was that it could become a new way of kind of conceiving of the industrial space of the day-like factory. So suddenly from an initial study on robotics, became very interested now in Buffalo and the history of the industrial loft. And of course, industrial lofts are a site for urban renewal because the industry is in its decline. These buildings are left over, and of course, the artists, entrepreneurs go into these spaces, and this is what really revitalizes downtown. But my main interest was somehow the idea that in this project, that space would turn from multiple objects populating an empty space back into a completely empty space. So this idea of coming into being and disappearing, of transparency through dematerialization, kind of resonated to me when Phil was talking about that idea of invisibility. In the second layer of invisibility, we just will really begin to talk about new glass technologies, smart glass technologies. This is a really interesting movie that Carla actually pointed out to me called They Made of Glass by Corning, and it's just showing multiple reconceptualizations of the function of glass as both information interface, but also as a common mirror in this case. And early in I think this is like way back in 1998 actually, this was an old project for a liquid crystal glass house that we did, which is simply just taking a piece of material that turns opaque and transparent. Switchable glass has been around since the 80s. And just building a house in which you can move the opacities and transparencies around wherever you needed. So you didn't need any fixed opaque core for your programs. You could just, if you have to go take a shower, you just basically conjure up an opaque cocoon in the glass. This is just a quick detail of an older project. But then I saw this amazing project actually by Carlo Leito and Keller of Hausberg Tarkovsky, in which transparency and visibility and glass became sites of imagery and information transmission, and not simply just a plane to see through. This Cogent project was actually what's beginning to happen in glass technologies is that transparency itself is beginning to become multifunctional. So just a real quick survey of glass that generates heat, glass that produces media imagery, glass that generates power from the sun, a solar panel, glass that goes from opaque to transparent, glass that fades in and fades out, glass that turns from clear to that in this firm, so at the last moment before I bailed on that whole negative life trajectory, I got a picture of the opportunity to design a roof plan for this building. And so I thought, you know, it'd be interesting to turn this thing into a stealth bomber. And I thought it was a joke. I sent it out, and I thought it would never get through. And then 10 years passed, and never thought of it until Google Maps came out. And I typed in Google Maps, and there was the building, and there was, it looked exactly like the RQ-170, the one that landed in Iran, actually, that the CIA lost in their spy plane program. But I was interested in this idea of a kind of a joke that suddenly became visible only because of the technology of being able to survey it from the sky became possible. So it's a joke nobody got because it's a stealth joke. But then I, you know, early started to get more interested in this idea of cloaking, and this is a really interesting project by BA Systems, which are basically thermal tiling that allows you to mask or change the IR signal of a missile sent for a night vision system looking for an enemy tank. And so basically this allows you to turn the tank into maybe a little SUV, or it'll completely disappear into the background. And of course Phil covered these ideas of optical metamaterial cloaks. And the cloaks are basically bending electromagnetic waves around objects to create a shielding space in which that object would basically disappear, and the background light would appear to classify that object without its visibility. Cloaks also on the acoustical cloaks, since the sound waves are also made out of waves, you can cloak those as well. And so I attempted to try to really kind of conceive of the architectural facade as an invisible condition and what that would mean. And this is a very quick sort of proposal for a series of mixed-use theater towers with theaters at the base cloaked in metamaterials so they're invisible, and then above that is conventional office floors or residences that seem to basically float in midair. And we did some quick simulations with the engineering department to work on cloaking a square plan, and this seems to be possible, so that is indeed a possibility of developing space which you wouldn't see. And I think the key idea of
scale what is considered nanotechnology. Yes, that's me. Thank you. So, as I said, I like materials that are performative, mostly smart materials. So smart materials are considered smart when they can react to an external stimulus with a material response. What you see here is a hydrogel that can absorb massive amounts of water, hundreds of times its own weight in water, and is considered a polymorphic material. So it actually responds to the chemical input of water with the change in shape that you can see here. Now, I already said that I have an affinity for the nanoscale. This is a carbon nanotube, and we've already heard about them from starting with Philip, and we've seen them a number of times. They're fantastic electric conductors, thermal conductors. They have so many properties that are just absolutely amazing. And we can infuse materials with them in order to give them very specific properties. So it's very similar to what Deborah is doing, where we're actually looking at a material and we have this desire to make it do something that it doesn't do. So we're starting to work with these materials at the scale of molecules in order to give them the properties that we think they were lacking to begin with. And my work looks at how we can actually design with those new materials and what do we want in these materials. Now, why would we want to change them and what does that actually change in design? Now, just to go back to the scale for a second, carbon nanotubes, they're very small. They're roughly 1.5 nanometers in diameter. They're several microns long, but just to give you another sense beyond the fingernail image that I showed into your head earlier, they're so small they can actually fit inside your DNA molecule because the base pairs of your DNA molecule are roughly 3 nanometers apart. So, as I said, we can infuse materials with these properties. And we can really start engineering the systems. But we have to, when we're asking the question, what do we want our materials to do, we have to look at the issues that we're facing in the constructed environment across all scales. So from the nanoscale, where we're actually putting these materials into another material, and we can infuse them into epoxies, for example, and then have an electrically conductive epoxy. And then it turns, like very much the concrete example that we heard earlier, the material itself into a sensor because I can run an electric current through this network of nanotubes that are all touching each other and conducting electricity through this physical contact within the material. But we also have to look at the design issues that we're dealing with at a global scale, even beyond, because the way that our planet works in relationship to the sun, we get these different climatic zones that you should all be familiar with as designers, because we work with them, we have to design for them. And we have to be able to really make these different connections of how all these different things come together, especially when we're trying to form interdisciplinary collaborations to create these new materials. So imagine just for a second we have this very specific relationship to the sun that varies throughout the year, which gives us the season, which is also something that Deborah mentioned earlier, and that in turn shapes our thermal environment massively. So we have these daily temperature fluctuations, and then in the interior of our environment, we're trying to really buffer that in order to create an environment that is more suitable for human habitation. So one of the materials that I've been looking at are actually phase-change materials that can take this energy and buffer it. They're really moving the peak temperature further away in the day in order to relieve the pressure on the systems that are running our architectural environments. And it actually can absorb the energy from the sun and store it and release it later. This is very beneficial in the constructed environment because we are responsible for a lot of energy that we are producing in the United States. And as you can see here, most of the energy that we're using is coming from fossil fuels, which we all know actually largely contributes to climate change. And when we look in detail at how much of this energy we're actually using on space heating and cooling, we can start getting a sense of what the responsibility is when we're designing for the constructed environment. So when we're asking some of these materials to do something very specific, I think it is very worthwhile to actually look at some of these major problems that we are facing. And since way too long, for the last decades, we have been really working with manufactured environments, where everything in the interior is controlled, and it's controlled by energy that has been produced in a not very sustainable way, as you can see here. So when we have these new materials, like paraffin wax, for example, which can be a component in these phase-changing materials that we're creating, we can really tune them to very specific temperatures that then in turn work with the very specific climatic zones that we're designing for. We can infuse them with some of these carbon nanotubes in order to make the thermal conductivity within the material system work better. We have to encapsulate them in order to actually integrate them into some of our building components, such as drywall, so that we don't have the leaking of the wax within the material system. But then you can also imagine when you look at this temperature graph, and this is specific to New York City, actually, not a single material can actually fit all these different thermal requirements throughout all the seasons. So there are researchers who are actually looking at combinations of different phase-range materials that are tuned to different temperatures in order to respond to different seasons. And as architects and designers, I think it is our responsibility to really look at these environments that the material composites are being designed for, because we actually have to tell people what we need, right? The problem is we can't just simply wait anymore for somebody to give us a solution and a product is being thrown on the market magically if we have never learned to actually ask for what we need. And this is one of the most important things that I'm trying to tackle with my work, that we are actually creating materials that fit all scales, that work from the global scale to the material scale to the nano scale. But it also responds to the human factor, because we are part of this environment as well. And we change our temperature, our core temperature of our bodies changes over the day as well. And this is something that we have to look at when we're designing. We're also designing for people who do, lives with certain activities that change throughout the day. Our productivities levels change throughout the day. And these are all factors that, as architects and as generalists, in a way, we actually can work with and design for. So when you can look at this graph now, with the blue line actually being the core temperature of a person throughout the day, you can start seeing how we can modify our thermal environment with a very specific combination of materials in order to fit what the bodies actually need, that we're housing, that we're actually allowing into our designs. So when I'm teaching, I follow a different lines of investigation. I look at materials that have been developed for other disciplines, and I see how I can actually integrate them into architecture and design. I don't only teach in architecture, I also teach in interior, in industrial, and in digital design. So I have ample opportunity to really look at the entire design environment when I'm looking at new materials. And the second line of investigation, I collaborate together with researchers who are actually actively able to manipulate matter. So I'm going to show a couple of projects that my students have worked on over the last years. This was a workshop that was held during the Catalyst Week. You can see a material composite here that uses a color-changing material that is tuned to body temperature. So at cold temperatures, this material was applied to the textile. At cool temperatures, it is actually black curtain. And as soon as you bring it up to body temperature, it will turn translucent and transparent. So you can see how the students are interacting through this screen and how light starts migrating through it. And it's really designed for the students to understand what it actually means to work with materials that change over time, that work in 4 dimensions. What does it mean when all of a sudden our bodies can interact with matter and really manipulate matter and really be part of the entire system that we're designing for? And these beautiful interactions were captured in this play that you can see here from the back where they were throwing warm water at the wall, but then there was an opponent on the other side who could simply undo the color change by blowing at it gently. And what does it mean but when we're thinking of how we're changing materials in the constructed environment, especially when we're thinking about it in terms of the thermal environment that I just described quite a bit ago, you can start thinking about how materials that change over time can actually be engineered and programmed to respond to a certain environment. So imagine you actually have architectural components that can change color depending on the outdoor temperature. It could be facade systems, or they could be roofs. So think about you having a roof that is actually black at cold temperatures and turns white at hot temperatures, and how that would actually influence the entire thermal behavior of a city when we're starting to think about cities and at the city scale, and we were talking about the urban heat island effect that is really quite a problem, especially in large cities like New York City. And it's all just within this material that is black in some states and then white in others. Now the question is though, why haven't we done that 10 years ago? It seems like such a simple material, we just paint it, why not do that? Well, the problem is right now, this material actually does not have a very long lifespan. And in architecture, we would like to guarantee that our buildings should work at a very minimum for 30 years, if not longer. So the problem is, as soon as we have UV light, certain chemicals, or very high temperature fluctuations, this material actually will not work anymore. And this is where we have to start these collaborations where we're working with scientists or the STEM fields in general in order to try and create materials that are really designed for the constructed environment. So we're not quite there yet, but there are many teams worldwide working on the issues of trying to give these very specific materials. In this case, they're actually nucleotides, if you're interested, and how can we design them so they work on a longer scale. And they're actually quite intriguing because when you look at them, what is happening on the nanoscale, it's really a tiny little muscle in a real way. It's a tiny little shape change within the molecule when the temperature is changing that changes how the light is actually going through the material. Now at my school in GIT, there are a number of researchers who work with color changing materials that can change to, depending on different stimuli, they can range from mechanical impact, they can respond to chemical impacts, they can respond to temperature changes. They can be indicators that you can, for example, add to a packaging, let's say a vaccine that you want to ship, and a vaccine that can actually spoil if it gets too hot. Sometimes you want to have an indicator on there that has a record, like a history that is programmed into the packaging simply through the material if the material reached a point where it was too hot. So those are some of the things that are currently going on at NGIT. I personally got very interested in the matter of materials and how they work on the nanoscale when I was working in my former office of decorating with artificial muscles and how artificial muscles can actually change the way that we design architecture. This is a dielectric electroactive polymer. It has two silver electrodes on a polymer core. The electrodes are applied in a correlated manner, and as soon as you apply current to this material system, the electrodes become attracted to each other and in turn squeeze the polymer, which triggers a shape change. It is not the most enormous shape change. It's actually quite subtle, and you can see this muscle flexing in the video here. The reason being is that the entire system depends on the electrode, and you can only deform the electrode so much before it actually dies, ruptures, and then of course as soon as the electrode doesn't work anymore, the entire system doesn't work anymore. So the challenge for this design that I worked on together with Peter Yaden was how can we actually take an artificial muscle that has a very small movement and turn that into a design in a constructed environment that can actually perform something for us. So this is the example that we came up with. It's the homeostatic facade system that has the silver muscle wrapped around a polymer core. And when you turn on the material system, changes shape and flexes the polymer core that it wraps around. It's a very, very light material. It's lighter, much, much lighter than my scarf. Like imagine a super silk scarf in terms of weight. So you can simply adhere this to a double skin facade system. And then through the silver electrodes, the material can not only block sunlight depending on the setting, but it can also guide it deeply into the room. So it can be a shading system, but also a daylight guiding system to control solar heat gain, but also visibility within the constructed environment. You can control the entire system very, very detailed because you can activate the screen at any point within. And considering how much glass we have in the constructed environment and how much solar heat gain we're battling on a day-to-day basis, and I think what I said earlier about the manufactured environments that we're having on the interior, where we're controlling everything with energy, these kinds of systems can only be beneficial. Now, I very much love working on this project, but I got a little bit dissatisfied with the material. In the beginning, I always thought it's me. I'm just not that talented in working with this material. I destroyed the electrodes so many times that are wrapped around the polymer. The reason being they're only a couple of 100 nanometers in thickness. So you look at them too hard and they really burst. If you touch them, the acid will corrode the electrode in no time. You can actually see, I'm not sure about the light levels here, but you might be able to see the material getting a little bit darker in here, which really is a sign of the corrosion. And of course, if the material is that finicky, remember what I just said, that we would really like to have most of the architectural components last for 30 years. If this happens to my electrode after a week or two, then I have to say this material is not good enough for the constructed environment. So what do we do now? Just like move on to the next material or say this is not going to work, or do we actually start collaborating properly? And this is where I really found myself in a position where being embedded in a research university can be immensely beneficial because that's already a network, like the first day of network for collaboration, and where we really can integrate the design field or architecture and design into the STEM fields. So there are many different kinds of electrodes that I was looking at over time. None of them were 100% satisfying, but I have not given up quite yet. There are many scientists who work on it. Some of them use actually carbon nanotubes that they can force into a coil to a very controlled system where they're buckling the carbon nanotubes that I showed you guys earlier. And then, of course, through that almost spring-like design on the nanoscale, you can imagine that you already have an electrode that could move much, much further, and they do that now. There were electrodes where you simply dab on carbon particles, or you suspend the carbon particles in a grease system in order to create these muscles. They do work, but they don't work for a very, very long time. So at the school we were running a number of experiments where we were trying out different electrodes, building new artificial muscles that you can see here. But it was still a very, very finicky system. And you can see how my students, Chris and Lisa, used the polymer that they dabbed on different kinds of electrodes. And you can see the testing that they did, and of course sped up by a lot. And this was a very long, long project, I have to say. And there were many times when they really made the muscles explode, or all kinds of things. And it's never a good thing when you see lightning in your studio. And I always keep on telling them, don't electrocute yourself, but they're not always as careful as I wish they would be. So, but they're currently actually exploring some of these materials for soft systems in architecture. So what they're looking at is all these different materials that we have. This is a flexible battery that has been developed in NGIT that can store energy. There are all these different flexible going to have a little sneak preview of some of the actuators that my students are currently working on, hopefully right now this week, that are integrating a number of different materials, such as the liquidize that I talked about earlier that can change color depending on the temperature. They come, of course, in different colors and they can be geared to different temperatures. And then they can be evenly distributed into soft matter, such as silicone. You can observe the color change of some of these pigments. They are technically, the molecules themselves would go to clear, but they're actually encapsulated in a tiny little polymer shell in order to protect the material, which is why they look rather white in this pigment form. So what the students were doing, they were mixing these different dyes and pigments into silicone that was then sent in a mold in order to create these new soft actuators that can change their shape in order to perform certain tasks in the constructed environment. So you can see here, that was one of the first actuator tests that a team of 4 students is currently still working on. This is only demonstrating the shape change within the material, but the actuator can actually go from blue to white depending on the temperature. So at warm temperatures, this is going to be a white actuator, and when it is cold, it will be actually dark blue. They are also experimenting with different luminescent materials that can absorb the energy from the sun during the daytime and emit it at nighttime, actually quite to great effect. They're new pigments that can last for a very long time, and only after 10 minutes of being irradiated with sunlight, they can already emit light for very long periods of time. So you can see how a lot of these new materials can be very easily integrated into soft materials, and then we can start exploring new applications in architecture that we have not been able to actually do the way that we have done them before. But as you see, we really need to be able to ask for the right kinds of materials, and that's why I really want to stress the point that as designers, we have to talk to the standards and we have to talk to researchers in order to make it very clear what we need. These are some of the examples of the collaborators, Safari Paul in the middle, who has been working on the color-changing materials that I introduced you to. Saul Mitra on the bottom, who is working on the flexible batteries that can be simply painted and then could be integrated into these soft robotic systems. And on the top you can see John Federici, who has been graciously giving me access to a nano printer that can print inks with very high precision that you can then turn into sensors that I can simply print onto all kinds of matter that are flexible. Some of them are even stretchable. So start thinking back a number of years ago when we were looking at the human genome. It used to be such a mystery when I was growing up. What is the human genome? What is the DNA? And what's its origin? And it's this really interesting project with the Human Genome Project that was established. When you imagine how much effort it took to decode that, and how many researchers were collaborating for so long, so closely, and they had so many agreements in place that would actually facilitate this kind of collaboration. So they would actually, publish their findings before, or share their findings before they were properly published, which is something that, as a scientist, you really don't want to do necessarily. That they all were going for this higher goal of trying to decode the entire human genome. So they just changed the way that they collaborated in order to get that task done and get it done in a timely manner. And maybe we really have to look at that as a case study and be inspired from that collaborative effort. So not only do we have to actually learn each other's language for these new collaborations, like what Mitchell was talking about earlier and what he is practicing, so by simply working together very closely, we really need to start understanding what our differences are and what we have in common in order to tackle a common goal. One of the initiatives that is actually being run here in the United States is the Material Genome Initiative that is trying to put some of these collaborative tools in place, where we're supposed to be sharing our findings as early as they did with the Human Genome Project. It hasn't quite taken off yet in the way that I was hoping it would personally, but I still think that there is a lot of hope behind that. And it really is trying to look at the design of materials and the process of designing materials in order to speed it up. So when we're thinking about, we're having a discovery, and then we're developing this material, we have to run a property optimization. The system design and integration follows after that. Certification, manufacturing, and then we finally get to deployment. Those are a lot of steps that we have to go through when we're inventing material. And the goal would be that we actually do that for half the cost and twice as fast with these new tools that the Genome Project is trying to put in place for us. Now, I think this is still very much geared towards the STEM fields, and in order to really get materials for the constructed environment invented and designed, we have to integrate architects in this process. And we can actually allow for connecting many of these steps very early on, tell them what we need, and then also actually work on early acceptance. We are the ones who are actually using these materials. So in order to go for rapid deployment, I think architects and designers can be very instrumental. And the idea would really be to cut down the time that it takes us to design a material. Think back about the base change materials that I mentioned earlier in the lecture. I think the first, if I remember like right, don't quote me on the date, but I think the first building that used the base change material was 1948, I believe, built in Massachusetts. Sometime around here. I think it was 48. And then when you start thinking about how in the last 10 years they have really advanced this material that we can finally find products such as drywall that has been integrated, that is a very long time. And it's partially because the collaboration is a little bit finicky for architecture because our buildings have to last that long. Other materials like you can see here Teflon or Velcro, they only took 2 decades only. So in comparison, I think the construction materials are actually rather lame. But I think if we are being integrated early on, we can really cut down on the amount of time it takes us to design a material and then actually really have it deployed in the constructed environment. And going back to one of my earlier comments, we really have to start thinking about that when we're talking about climate change in the constructed environment, because we are looking at some serious issues that we're facing across all scales of design. So from the building scale to the city scale, we're going to be looking at an impact through a changing climate that is quite staggering. We're still dealing with the output of carbon, which is directly related to the temperature anomalies that we're experiencing and that we have been experiencing for a while. So when we're looking at the issue of climate change in the constructed environment, we're really looking at 2 different scenarios right now. If we keep on going the way that we used to, if we keep on using the same kind of energy from fossil fuels, and apparently thanks to fracking we have an abundance of that for a very, very long time. But this is going to keep on changing our climate massively. And changing doesn't always mean that it's getting warmer. It can get actually rather cold in other areas. So we're really having to look at curbing the carbon output, but also we also have to look at adaptation to climate change that we cannot stop anymore, and mitigation. So in the light of that, I think materials that we look at, especially materials that can change depending on their environment, smart materials that can react to an external stimulus, like solar cells. When we have sunlight and we can use solar cells to produce electricity. We can use materials that change their shape depending on temperature. Those are all materials that work with ambient energies that are abundant, that we do not have to dig out of the ground and burn. And I think in order to do that, and to do that effectively,
Studios in New York, also in Lisbon. She's taught at architecture studios and seminars at UPenn, Pratt Institute, Cornell University, City College of New York, Columbia University, and she has practice and academic endeavors that focus on the convergence of urban phenomenon, ubiquitous cultures, digital communications, and the generation of political and cultural innovation. Her publications include Four Lines, City Fragments, and and she also has projects that are ongoing residential and institutional projects that are being built today. Exhibitions and installations include Suture at SciArc and True Romance in Stuttgart, Germany, and Young Blood in Lisbon, Portugal. So without delay, please Carly.
There's no doubt that the idea of programmable matter is a fascinating one for many fields of thought and practice. Among other things, because of the way in which it can profoundly transform the assumptions about drive and direction of development of these fields. The questions on the relationship between definitions of matter and the discipline of architectural design mirror to a certain degree the questions happening within other disciplines connected with generating matters taxonomies or engaging material development. Just in the last decade, we have seen how engineering and material sciences departments struggled to keep some sense of their sub-departmental categories. Categories which have ensured continuity in regimes of expertise and knowledge, and the shifts as nanomaterials and metamaterials profoundly destabilized foundations of expected behavior, trait, source application, and the whole disciplinary regime of research. If many developments in nanomaterials and metamaterials seem to be bringing us back to the exploration of basic universal problems that have almost infinite applications, how to improve a lens, for instance, and simultaneously to revert altogether to inversions of natural phenomena or to hybrids and to problematic of characteristic or trait, this also means that they bring us back to the idea of design as the original material in a perhaps Cyril Stanley Smith way, and several of us have already mentioned this today. But this means that it is with the pervasiveness of connectivity more typically encountered in matter. To put it simply, the consequences of programmable matter to ecology, economy, social, and several other dimensions of human and non-human life. Similarly, in the field of biology, there is a displacement that genetics promises to do in what concerns taxonomy or categorization and the deep transformative capabilities implied in biotech practices. While genetics knowledge can reframe concepts of origin, relationships, and enable future to the formation of entities, biotech in all matters of design discipline more directly intertwines or splices processes of evolution with the speed of cultural time. There's a clear triangle between matter, materials, and design, where the impetus for understanding primary rules that govern a system or entity is blurred with the cultural pressures of design intentions. We seem to be too caught up in the famous Marshall-McLuhan loop, whereby we are shaping the tools that then shape us, which is actually a paraphrase of Winston Churchill that is more architectural, which is we shape our buildings and they shape us. The questions I pose on the abstract of this response, which motivated the event, largely reflect the problematics raised by these questions of discipline and design within fields of science, and how these have strong implications for all other disciplines of the time. These mainly pertain to decreasing neutrality of materials, be it through an increase in our perception of matters and materials' inherent connectivities to environmental processes, connectivities that were before perhaps invisible to us, as well as a loss of an inert character towards a proactive agency embedded in designed composites or assemblies. This can be a new moment in history, mainly because of the way in which this implies on questions of the implication that this has on questions of power, authority, and property. And implied in this evolution, the question as to new characters or qualities that can emerge from it. Could programmability produce undesigned new ranges of controlled passive behaviors, or new forms of networking and integration that produce unanticipated cultural agency and even organizational will? For instance, what kinds of new governance models exist within innovative forms of political power that integrate increasingly embedded forms of surveillance, tracking, and analysis over every human and non-human subject? In the past 5 years, I've tried to experiment with these questions through academic research and work with students in what I've called the Programmable Matter Seminars in the Cloud Studios. The main issues that I've just been referring to drove the Programmable Seminar through historical performances of matter. To this goal, though, it is fair to say that if new definition of entities blur with the problematic of the definition of particle, so it happens that new definitions of the whole blur with that of the aggregate through problematizing communication among the parts. The cloud studios focus on microstructures that encourage the rethinking of hierarchies and hierarchical bodies for the ordering of space, material, and information. As well, they tend to create a condition of transversality, a pervasiveness of repetition that can act like a fog matter, capable of degrees of transformation, such as the terraforming of existing landscapes, overlays of performance within the same entity, creation of new hybrids of environmental space. The cloud architecture studio examples that I show here were from studios that had three themes, and they're relevant to the current Anthropocenic age we have stepped into. They were clouds of assembly, disassembly, and reassembly. The first studio, the Cloud Archive Institution Transversity, looked at design of structures with the capacity to create or inspire novel forms of institution within or across other environments, being both an archive, library, and an education promoter of protocols that would ensure collection of memory history, conservation, repetition, distribution, and platforms for the generation of new knowledge. The second studio, Cloud Disassembly, looked into the architectures that could disassemble other architectures as well as themselves. This was a study of the architecture and urbanism of large temporary events, World Cup, Olympics, and also World Expo, among others, and their promises and shortcomings economically and culturally for their host cities, as well as in the larger context of global awareness of buildings' larger environmental impact. The third studio, Cloud Reassembly, proposed an inquiry into the possible new structures of order that can be found or recreated in scenarios of catastrophe or disaster in the preparation, duration, or aftermath of radical cross-sectioning events of destructive force. In terms of cloud precedents, in the history and culture of architecture, the precedents for this kind of transversal approach are found in several sides of the aisles, so to speak, ranging from concepts of the megastructure, such as the ones from Rainer Banham, to that of global energy networks, such as like projects from Mr. Fuller. Many of these cloud precedents are easy metaphors given their ambition of transversality to other systems and their investigation into materials and programs. Notwithstanding that, the cloud studios tried to create new kinds of formations that would more intensively play with a distributed character and its sensitivity to environmental conditions. Formations that could become invisible, be torn apart by crowds, aggregate into rock, or dissipate into thin air, all the while keeping concepts of integrity alive, at least for our discipline that's relevant. This new definition of entity invariably borrows from practices that for long have been trying to pack intelligence into increasingly smaller autonomous units. Sorry, I can show you this. Did I? You should be able to see. Yes. Mostly military, but not only, research on micro-robotics and drone technology are examples of other fields interested in micro-performance. The new definition of aggregate or communication between parts also creates the need to digest the vocabulary and knowledge of media theory and media studies that have articulated conceptual and technical relationships for the domain of communication, medium, channel, noise, and ways in which these bypass considerations of content. A very centralizing concept for the cloud studios was that of the spine object. So these are some more of the drones. These are the hummingbird drones, which permit a very specific kind of flexible flight. And they were real and differentiated micro-autonomy. How could this be used to create real networking potential in objects or environments? Which scales and processes could these designs manage or influence? And so this is one of the examples, and it goes in the shell too, of what would be a spine in that particular future, so not, which is literally objects that contain their own history. So as soon as you have a reader, you can read what the object is broadcasting. And of course, when you start to have several elements that are both objects and readers, you start to just have pervasive broadcasting and reading. I'm just going to go fast on this. In the Cloud Assembly Studio, which dealt with archive typologies, students engaged the shifting relationships between buildings and institutions and the role that buildings, spatial constructions, have played and can play in the production, storage, and distribution of knowledge, while understanding is often engaging as well as concepts of symbolic, concepts of the problem of the symbolic or of that of the representation. In the fields of material sciences, cloaking materials and systems are a very unexpected yet very compelling consequence of the study of metamaterials. One of the projects in the Cloud Studios by Bradley Dunn, which should be here marked, asked what could happen if the application of this effect could happen in a more pervasive way to generic space programs such as configurations and or subdivisions of office spaces. Okay. I have his name all over the slideshow, so anyway. Or what could start to happen to landscapes if larger programmatic shells could envelop them? The issue with cloaking is that the effect is produced through the diversion of light rays, and therefore changes in perception could potentially have energetic and other informational consequences. The typologies formed by design would, in this manner, have a series of gradients of effect that can extend far beyond those linked only to perception. Well, I think this is sorry, I'm just going to. Sorry. I just, I think there's a part in
Don't worry about it.
Yeah,
That's all.
correct.
We don't,
yeah. It's cut, it's highly cut. So that's Bradley Dunn. I just will articulate very well the name of the student because it was marked over. So these are some of the examples of cloaking that Bradley Dunn did. So the studies on how to create different kind of cloaking boundaries, and then what the kinds of office spaces could be created, or subdivisions would be created, and of course he created an entire possibility of program for that. The Archive Cloud projects also dealt with other kinds of transparencies, those that focus on communication between parts. Something is wrong here. I'm not sure what's happening. Sorry. Let's see if I can go back. Otherwise, I'm going to miss huge parts of. So Archive Cloud projects also dealt with other kinds of transparencies. Those that focus on communication between parts or processes that reveal hidden or virtual aspects of programs. In Vivian Berton's project Hydra Index, an active weather system connecting the information space of several agencies, including governmental, NGO, research labs, and park activists, helps them collaborate to get an inside multi-sourced picture of the environmental makeup of a region. Vivian used the model of the hummingbird drone to model much of the way in which these pissed out clouds could literally fly. The project then hovers over Parana in Greece to produce impressions of that information for the population. consideration of the well-being of its population and environment. Perhaps this could be some kind of a new form of a gentle but firm policy done by environmental activists today. Another example of an assembly cloud, Jennifer Bloom's project Star Constellations, shows the way in which a web of networked 3D pixels become a map of materialized work relationships in a biotech lab facility, connecting researchers with their information and with each other, reflecting trends of up-and-coming and phased-out research. On the Disassembly Cloud Studio, we engage tectonics of the temporary, of light construction, and also models of the aggregate, of erosion, and of the ruin. In the work of Gillian Crandall, the sentient event, Olympic athletes are technologically augmented to become agents that map sites and deploy strategies in them. Deformed to their sports, athletes can be activists for collectives, be it populations or other agencies. Deploying physical systems in situ for political and environmental change under the umbrella of nation cultural exchange, political protocol, and propaganda. In the case of Philip Vernon's project, Irradiant City, the creation of a peer-to-peer network in areas of Cameroon without electricity through RFIDs deployed in different forms and aggregates of material, as for instance stickers, sprays, or concrete aggregate. These would act as information relays across vast landscapes and lead to an in-depth analysis of existing patterns of communication. The Reassembly Cloud Studio, or the post-disaster cloud, engage properties of resilience in both human constructions as well as natural formations. The studio very directly reflected on the predicted challenges of the Anthropocene era, where layering, recovery, and transformation will increasingly dominate the tectonics of architecture and design. John Baker's project, Cloud Power, establishes a system of relays for the upcoming Witricity, which is wireless electricity, which creates a new economy of storage through use, pairing users that otherwise would not intersect in activities across a common urban fabric. In Josh Berger's project, materials sorted by natural disaster are reassembled into new aggregates, pressured into units of reconstruction or nascent orders of occupation for their home landscapes. In Michael Villar's project, he creates prototypes of effect for a material that indexes stresses by speculating on the type of erosion that would occur from a corrosive metamaterial that acts along magnetic fields or electric field vector lines. So there's some tropes that were found in a lot of the work both of research and the work with students and even in our practice. One of the found tropes was that the body is still a central figure. It is not only a measure but now also a carrier, a construction material, a distribution corridor, and the site and the architecture through each site is measured and revealed. And this is clear in the work, for instance, of Gillian Crandall with the athlete, where the bodies of the athletes are the place of projection for all the gains of urban fabrics. As well, that architecture becomes more and more a problem of a networking mode or platform. That architecture is used to relink scattered pieces of landscape that are part of some kind of common abstract body, cultural or otherwise. So a boring distance, these cloud architectures are materializations of virtual networks we want to create that link remote communities together, for instance, or can analyze or generate or distribute or characterize space and information on a particular locale. The other one still is the fact that more and more what we have is the map becoming the final content or message of architecture design. So architecture, if it is a kind of an info aesthetic of a site, reading present and possible futures made by cultural, social, and political exchanges. We know that then scenarios are drawn to build access maps of sites at the edge of their potentials. Those maps become multiple cross-sections of performances, layers that are never all co-present nor work synchronously. The mapping of consistencies in a site becomes a way by which apparently unmatchable narratives find some kind of common deployment units. So, a kind of a conclusion that I wanted to withdraw, I wanted to actually start with a very small quote of a very recent article by Rem Koolhaas in Art Forum, where he's finally talking about smart cities. It's like, we finally realize after everyone for 10 years has been trying to work with them, is they realize they scenarios that have contemporary or new future characterizations of populations, materials, and information. And their designs, or these designs, operate within environmental frameworks that are defined by different predominances or hybrids between access to high-tech apparatus or the potential of resorting to low-tech apparatus. And these are all just types of intelligence, of access, based on access. Given Cloud Studio's interest in material research and invention, the question arises of whether to consider scenarios where transmutation of matter is possible or where radical pervasive intelligence and communication have been attained. For instance, scenarios where smart dust or utility fog exist, for instance. It seems that these are very different things, and they would imply very different questions of design than the ones that pertain to contemporary or near future condition that we can actually imagine and design for. For example, scenarios where quantum computation would be a pervasive reality imply a speed of processing that profoundly transforms the nature of problems, or ambitions of design itself as an activity. Such extreme processing, or the transmutation of matter, may indeed surpass the need for design as we know it today, and the idea of a discipline of design as a technology in itself. And its very value concept as a practice would see a great paradigm shift. It seems that this in itself would be a singular paradigmatic topic for design as a practice, as it so far has installed itself in the delay, so design has installed itself in a delay or an imperfect connection across reality's informational and energetic databases. So I think design and architecture design especially, there's just technologies that are installed in a particular time frame where we have delays between things. And while that exists, design is that technology. But other things might come true. If architecture design is made of inert materials, its capabilities are different than if it is made of media-linked active materials. The possibility of the latter brings to the forefront of the discipline and practice different types of actualizing tectonics of the discipline and practices, often virtual bodies. A contemporary broader discussion on the generation of knowledge centers on the distinction between the humanities and the sciences and their influences on cultural development. There is a tendency to distinguish these two branches by methodology, with a contemporary preference for scientific methodology, or that which delivers knowledge through deductively born facts out of experimentally confirmed laws. There is much to be done in revealing the creative aspects of the generation of knowledge within scientific methodology, namely, for instance, the role of abduction in the scientific method, which is a parallel process to induction. Induction is called the Berry hypothesis, so the risky hypothesis. And this depends on the practice of a highly cultivated tradition through the synthesis of learned law and experiment, as well as a broad experience of reality's processes through, among other things, cultural models that direct perception, perhaps in particular ways. Carl Schroeder's concept of thalience is an attempt to think of what could be a discipline of thought after science as we know it. Quote, what if you could separate the activity of science from the human researchers who conduct it? Automate it, in fact? Imagine creating a bot that does physics experiments and builds an internal model of the world based on those experiments. It could start out as something simple that stacked blocks and knocked them over again. Later models could get quite sophisticated, and let's say we combine this ability with the technology of self-reproducing machines for non-human machines. Here's the question that leads to the notion of thalience. If they were allowed to freely invent their own semantics, would their physical model of the universe end up resembling ours? I don't mean would it produce the same results given the same inputs, because it would, but would it be a humanly accessible theory? End quote. So I think this is more than a statement, it's an interesting question. I mentioned this example not to bring the usual question of the human versus the automated world, but to invoke a reminder of the way in which we often use models as stepping stones in attaining comprehension of processes and then to actually create and test more processes. In architecture theory and practice, we often find discussions on comparable realities, for instance, between architectural space conceived as background for program or as program itself. And this often creates a binary between aesthetics and performance. Like all other binaries, this misses the gradients and synthesis present in the performance aspect of aesthetics and, of course, the aesthetic value of performance. In both processes, one, the scientific method based on experimentation for validation of observation, and the other, the design process, which is interested in an abstract correlation as a mode of evaluating the success of a synthesis. There's non-pragmatic scientist and human being in general, so kind of an elite that lived in the clouds. At a time where science was actually being tested in labs that were mounted in the domestic spaces of scientists, literally the kitchens, he was condemned by something akin to proposing a belief system, very near religion, which in this case was called oxygen. And then he was punished by society for being interested in ideas that had no practical applications, supposedly, which were invisible and which needed special complex tools, objects, and calculations, were both his tools, to be measured or even perceived. I bring this last example as a call to arms in what regards the role that both scientists and designers kind of have to assume or invite themselves to be as cultural agents. And I would like to propose that the tropes which I found here in my research practice and also in the cloud studios of these last years seem to offer perhaps some emerging new vehicles that can be seen as modes, tools, ways to navigate the new paradigms of sorting, layering, and shifting bodies of landscapes of the Anthropocene, or even perhaps of the post-Anthropocene areas that we are imagining or stepping into. Thank you.
Yes.
So we have like about 10 more minutes to just have some questions from the audience and from participants. I mean, I lost most of my class. I don't see second year here. There's like 3 people left. So you guys are the only ones who are going to get good grades. The rest, unfortunately, are going to suffer quite a bit. So, I mean,
Their proposal on this call.
yes.
It's not
It's not full hour. We have plenty of time. Did anybody want to pose some questions? I can make some observations. I'm going to make one observation that I think is really seminal, that really is inspiring. And it seems like in practice in the past, you have an office, you have to feed the office work, and you have
turn. I mean, we've been stuck in computation for 20 years, since the advent of CAD and what computers can do, and then getting into the fabrication system and feedback loops between CAD files and fabricated systems and their relationships. It's become very a kind of convincing and mature design space. So now we're sort of weaning ourselves off of just doing simulated digital-based models into new disciplines, new physical territories that are involving materials or involving actual biology or genetics or nanotech, something that we don't have a bunch of computer models for necessarily. Well, there are some.
I mean, with Martina, you know, I'm using off-the-shelf servos, but you're designing the servos themselves, right? By building these fluid muscles. And when can I get to use that on my robots? That's my question.
Well, why don't you come to my review on the 30th?
Okay. Sign me
From
up.
2:30 to 6.
Oh, okay.
Well, it's going to take a while before some of these things are really going to find their way into architecture. I think what's really shaping the research on that front is actually that we're looking at problem-based models. Right? We're looking at a certain issue in the constructed environment, like climate change or energy consumption, and that those are problems of a very high complexity. And there is not a single discipline that can actually solve that. It's just impossible. And then that, together with all the new networking tools that are emerging, where we can remotely really collaborate or share a symposium, even though it is in London. With all these new tools, we can really create these interdisciplinary, very large research teams and collaborations.
So,
But it's all about like a lot of these interdisciplinary endeavors come from problem-based research, where we're really trying to tackle something that merits our concern.
Yeah, that's a good point. So it's more, it's not even a problem, it's really a threat. Climate change is pervasive, it involves everyone from economists, policymakers, designers, engineers, it's the whole gamut. And that if we don't solve it, it's the end of the world kind of thing. So it's definitely a problem that requires real innovative, shift-changing, paradigm-making experiential research and design and ideation. Like we got to make it's something. It's wicked. We may not solve it.
No, I think I mean, I've
Well, we
tried
definitely
not to
will.
become a doomsday maker,
Right.
right? Because when you look at the problem in detail, it's a really big one. But I think if we really work together, we can actually tackle it. But it will be a interdisciplinary goal.
But it's interesting because, for instance, the case of the muscle that you were working with,
Which one?
so the one that you tried to, so that's exactly the point. So the idea of muscle, of a muscle that will be very low energy consumption, and that then you try to apply it to very different things. That in itself is a connection which is not completely problem-based. It's not a very definitive, specific problem. It's like a conjunction or a kind of a aura of problem. It has to do with low energy, but then it could be facade, then it could be something else. And as you develop ideas of the muscle itself and what it operates on, or you discover that it's finicky or stronger in particular ways, it's almost as if the modes by which you make it stronger because you look at a particular application can actually start to drive it in a particular other direction. So it's not completely trying to solve one problem of facade. It feels that it has this kind of, it's constantly branching or something like that. So it's problem or topic based, but not completely, it's not a problem solving issue.
It depends. Like, I look at materials mostly in order to actually address issues of merit or concern. I mean, if they're pretty, if they do something really cool, like they do this, even though that translucent color changing curtain isn't necessarily anything that is related to climate change or energy consumption. It's such a seductive material that how can a designer resist playing with it? And
bit more ahead of architecture.
And the medical,
Yeah, medical field.
oh,
in terms-
absolutely.
yeah,
But
so-
even with the research dollars that they're getting, they.
Yeah, that's one thing,
they
yeah.
will
So
research.
one thing that, how can architects learn from doctors, and how can we kind of catch up with their scientific progress? You're talking about from transportation to nanotechnology to robotics and everything else, right? How can we learn from them?
I think,
Yeah.
I think it's, if we're talking about curing cancer,
Yes.
that is something that definitely nerds are concerned. We may all probably know people who have suffered from cancer in one way or another, and we may be very close to people who. So it is very easy to raise awareness about that and raise funds for that. And when it comes to climate change, we have done a lousy job to actually really explain what's going on and why we need to put effort into that kind of research. And I think in order to learn from, like, or as you say, to draw the parallel, we can definitely learn from the medical field by just being very frank about what's going on. And we really have to educate the public to tell them that, architecture is actually responsible for a fair amount of climate change.
I think it's more invisible. I mean, I think the problem is more invisible and the urgency is more invisible. Right now. Yeah, no, I know. But it's more invisible. It's more invisible than being in a family where someone has died of cancer. And just knowing someone that has died of cancer. It's just much more invisible. I think that's maybe a problem. And so also innovation is the edge in a lot of other disciplines where architecture sometimes is not. In architecture you can actually be more economic and more environmental by being less innovative, high tech, by being more low tech. And so it's sometimes it's a very kind of difficult kind of balance to register between these things, because in a lot of other disciplines that kind of frontier that is constantly advancing can really show why it is valuable.
I just one thing of hearing I came here today, very enjoy your presentation, everybody's, but how, let's say, just to twist a little my question, how can some of those fascinating, kind of portable cars could be manufactured, become really the product that to make money? It seems that there was a huge gap between ideas and commercial product. In a way, kind of, sort of Terreform that kind of ubiquitous, and everybody has one. And how can personal transportation become mass produced and be able to recruit kind of
Well, okay, so I think that's a great question. Cell phone technology, telecommunications, software, that's the R&D for something like that is 5 to 7 years from a napkin sketch to you can purchase it. It's that quick.
I see.
Like the Apple Watch, a wearable, we can laugh at them now, especially these gold ones. I don't know where that stuff. I'm sure in Buffalo it's going to be branded. But we will, in 5 to 7 years from now, wearables, things like this will become much more available, if not everywhere. Vehicle technology is 15 to 20 years minimum from a change in sketch and base technology, such as hybrid electric or fuel cell, before you can buy one on any lot in the United States or Europe or Asia. So it takes a lot longer to develop that as prototyping and to do bulk production. Architecture is even worse because we build buildings, and that was mentioned before, we expect the roof to last 40 years, the boiler heater to last 30 years, the practice for 10 years before you actually start making headway in the field itself of architecture. You start opening up new doors and having replicatable experiments that other architects can take and use as a kind of a system to be deployed in their work. I think that pedagogically speaking, we need to have a stronger track of more doctoral work in architecture that goes beyond just doctors of philosophy who are working in history or history-based kind of systems. So I think that we certainly can do it. We certainly can graduate a lot of architects that just want to build buildings, a professional practice track. But there's a lot of talented, hardworking people that should be in labs fully funded because it's the same PhD program or doctoral program as you get in engineering, physics, psychology, what have you. And it's run by a doctorate with doctoral students. And the transition has been very difficult to see happen. But it takes that amount of 7 years of working on a muscle before you have something new to say.
So in a way, proposing sort of paradigm shift in academic setting.
Yeah.
Yeah. But what you seem to be doing seems to be sort of approaching to the more idealized condition to close this gap. So that architects can be more productive in terms of producing prototypes.
Right.
Yeah. If architects also can become also the entrepreneur, meaning to produce some actual materials or vehicles.
Right.
That would be great. But those are far-fetched, right? Sometimes facilities not far-fetched because not every architect can be an entrepreneur.
That's true.
Yeah.
Or wants to be.
Yeah. True.
Yeah. No, that's true. The cars that we developed, we were, as architects, we were not engineers, especially automotive engineers.
Yeah.
But we ran circles around entire companies. This was the lab at MIT because they were so focused, they had such blinders on, they're working specifically on roof brush or B-pillar design or carving. Like the idea that if you come in and rethink the system, you'd be fired or no one would take you seriously. But architects are great at getting the general physics of almost any discipline and creating a storyline and a rationale for why it fits, what those changes are, and what those applications would be over increments of time. And that capacity to think, the design thinking that we do so well is enormously powerful. And we need to show it off in more and more fields. But we somehow, we're a little bit troubled by it. I don't know. We don't value it as much as we should. We do, maybe in an interior sense, but I think we should really go out and tackle other fields with that kind of thinking. You can call it visionary or impractical, but you wouldn't have these cell phones if it wasn't for science fiction writers talking about something in Star Trek. You have a phone that communicates across the globe and tells you what's in the atmosphere and what the plants are made of. And that is a design narrative, it's a thought structure, and became very valuable into mainstream thinking to allow something like a smartphone to be acceptable, and people would say, oh yeah, I know what that is. Bad visions just collapse and no one pays much attention to them. And then there's visions that probably, we're still not there yet. Whether it's traveling to another star system or Le Cube or Le Deux, these beautiful structures from the French Enlightenment that we're still not building for various reasons, but they're in every history book in architecture.
But
I think it's a
actually,
tremendous-
I'd like to ask Bill, how far are we till getting an optical metamaterial cloak for visible light where we can have a wall that we can't see? Do you see this in 5 years, 10 years, 20 years?
I don't think so. I think what's interesting to me is how the concept, the science fiction, or really the magical concept of invisibility has got brought into this area, which is really about, some people want it to be seen as microwave engineering or optical engineering of some description. And it's very interesting that it seems that this science fiction trope is motivational factor for people working in this field, that it's a dream, it gives them something to shoot at. But it's problematic, I think, when you start to bring those ideas into something scientific, because it gives you the idea that maybe one day we will make things disappear this way. It's clear, I think, that we can't, that the optics just doesn't work. That you may well be able to, certainly you could use this stuff for other things. You could use it for optical computing to sort of hold up and divert light in some ways. You might be able to use it to some degree to camouflage things, to reduce the radar footprint of a smart aircraft. But invisibility is something else. Invisibility is about magic. It's a legendary attribute. It's not something you can import into science in that way and think that it's a technological problem to solve. I think there's I don't think that the people doing this work are mis-selling it. That it's a hook that they can hang their ideas on and it gets the idea across. But it's more problematic than is sometimes supposed.
One of the speakers here today that she had to cancel for another commitment, but she's in the UB Department of Optical Metamaterials, and looked at the NSF RFPs for that research area, and they're asking, literally the government is asking for a paint you can put on an airplane that would just render it effectively invisible to light. So that idea is heavily researched, heavily funded area of research. So I'm wondering, is that true though, that it couldn't be done? They seem to be taking it very seriously, that it is an engineering possibility.
Well, I guess that reminds me of you hear similar things coming out, certainly of military labs, of people asking for anti-gravity devices. And people, you will find people in, I don't know, I shouldn't impugn them, but the Marshall Space Flight Center or something working on this stuff. There have been people doing that. Doesn't mean that it's possible, doesn't mean that it's remotely feasible. But I think that's the kind of idea that will come out of this work, that somehow you're going to get a paint that is going to make things vanish. I don't think anyone working in transformation optics can see a way to get anywhere close to that, or that it's even a target worth shooting at. I can't obviously speak for what's going on in military research. There may well be people looking into that idea, but I don't see how they're going to get very far with it. I think at the same time, it's perhaps not a terrible thing that people are I don't think it is a terrible thing that people are suggesting things like that. That you've got to have someone to put these ideas out there, just like these guys who are working on illusion optics. It's this kind of science fictional idea. There, at least, you can do the theory and show how, in theory, you can make this work. Whether you could get a material that gets anywhere close to it or not, I'm very skeptical about it. I think one of the things that you see coming out of metamaterials is how once you really start to take these sorts of visions seriously, you see how compromised they're inevitably going to be. And that perhaps, that's not the way to get the best out of what these ideas and this technology can offer.
Are there particular lines of research within that actually have to do with the diverting of light rays to work somehow energetically with them? By concentrating them, for instance. Because that's one of the things I haven't seen well. I'm just online, right? But I haven't seen one of these departments that is working with transformation optics using the diversion of light rays to work with energy.
Yeah, well, no, it's a very good point, and there are people who are doing that. There are some groups in China who have been working on the theory of making things exactly like that, of concentrators rather than diverters, I suppose you could say. It's entirely possible, it's completely feasible, and that makes a lot of sense. it's really another version of, you talked about the use for new types of lens. You know, this is really the same kind of thing. So, you know, I think that makes a lot of sense, and I wouldn't be at all surprised if we see something of that sort starting to appear, if not in optical, then certainly at longer wavelengths before very long.
There are actually some examples where they're enhancing solar cells by redirecting light and channeling it. It's a little bit like the RTI case facade system, where they're really concentrating light on this one solar cell, but they can do it on the molecular level as well, right? So they're actually taking a material where the light goes through and it goes through the sensitive, photosensitive parts of the solar cell that actually generate the electric current, but then it actually, everything that passed or went through there without being hot, it's really directed back into in order to boost efficiency. But when you say about the metamaterials, when you look at the different wavelengths of light and you look at the nanoscale of like how many nanometers they're actually apart, I have to agree with Logan. I find it very hard to believe that we're going to be able to have one material that can actually manipulate across all these different wavelengths. And as far as I understand, the military research or the call for innovation or invention on the sector is really confined to a very particular wavelengths of light, like beta or infrared. So basically, you do make things invisible to certain technologies, not our eyes, because our eyes are actually more sophisticated in detecting different things. So you really have to basically run into the tank or stand right in front of it to see it with your own eyes, but like all your instruments can be blind to it. So I think we really have to be very careful with how we actually define light. And when we say it's like invisible, like what kind of wavelengths are we talking about? That's the question of the materials that we really have to answer first.
Very often, with broadband technologies like that, where you're seeking to have it work across the whole range of wavelengths, it's certainly for something like a solar concentrator, you don't need the kind of finesse that you would be talking about to make something even approaching invisibility. Some of the examples I showed where you're basically just using a block of calcite to make something a little bit invisible, and you can use the same crude methods to do some of these things. Those are the only ones that really work across the whole visible spectrum and beyond. So I think that's probably the message there, that if you're looking for an application like that, you don't need something quite as high-tech, something as highly engineered to make it good enough to work.